Morning there, ladies and gentlemen. Okay, so today I probably don't really need to talk a whole lot. Isn't that nice? So you won't have to listen to me babble on. I'm looking at Google Earth down here. That's my hand cursor. So we have flipping vortices. I think that's what I'm going to call this video. So we wondered if, the poles could flip and things like that. No. However, apparently the vortices can flip. And, we see that when we put when we go up here to view, we go to grid, and we put our actual equator, did I call it equator? The equator in place, you can see quite visibly, without any difficulty at all, that the Lake Victoria vortex is beneath the equator, meaning that it's going to be driven by the Antarctic vortex in its rotational direction. And, and you've got North Banda Basin, which also falls beneath the vortex, beneath the equator. The difficulty we're going to have, and I kind of had my head up my butt the other day when I made the other video, where I'm like, oh my God, look, it's really close to well, of course it was close to the equator, and actually like right on the equator, because the 45-degree perimeter in this circumference you see here on the yellow line is based on that top dead center location that I'm looking at for this particular circular formation in the Earth's surface. Naturally, if you do that, and then you go up here and you make this circle at 45 degrees, have a tangent that meets that tangent of the very first circle, your equator is going to wind up right dead top of your vortex. So the inaccuracy that I'm showing you here is that though this is the top dead center core of my vortex, it's not the equator. And because of the direction of rotation being opposite from Africa, that means it's telling us that this, at the time of the event that caused this vortex to form in the shape on our planet, this vortex was closer to the North Pole, which means we would be looking at something more like if we were to, I guess I was going to level it out between these two, but that's silly. It just means that at whatever orientation it had been at that time, the equator would have been down here as opposed to up here. So if I go back and turn on my grid, now I have my equator up here. Our equator would have been somewhere, I'm going to move it over here. Now that's my easting. So south, it would have had to have been really close to where our 10-degree latitude is in the southern hemisphere. Right in there. In order to put that vortex up at the top, which means its mate would have been below. I don't think I did a circle for the mate. I didn't. So, haven't gotten that far yet. I was like, Anyway. It's there. So there you have it. Flipping vortices. So at some point, how does this affect us? It could affect us quite dramatically, but not in the sense of the North Pole shifting like 20 to 30 degrees over here just out of the clear nowhere. Oh my God, the whole planet went thump. Well, our continents don't migrate quickly enough, fast enough to throw the planet's balance that far off. It just doesn't happen. Not when you have so much force striking the solar system. This is what makes solar systems flat. It wouldn't be flat if it wasn't for rear pressure and forward pressure. So your forward pressure is your bow wave striking the solar system. We kind of figured that one out. But our rear pressure, which makes our solar system conical, is the pressure that strikes our solar system from behind, because it's a rear pressure. I know. Anyway, it's the galactic energy that comes from there. So, and when I say galactic energy, I'm referring to the supermassive electromagnetic gravity waves. They're combined, so you have the supermassive electromagnetic braided field ropes, and I'm calling them ropes because they're like coiled into waves, and these coiled waves generate their own gravity. Why? Because gravity is the vacuum of space, and the vortex is what generates these vacuums of space. So this is why around our equator, our vortices are, and I may have gotten this confused before, in the same way that I get my, which way does the rope drag when I spin a certain direction, I have that same problem with, anti-cyclonic versus cyclonic. So here's the point, folks. Cyclonic means it's a cyclone on our planet that is sucking things that are on our ground up through the funnel and throwing it out. Fish, whatever. When it's raining fish, that came out of a cyclone. When it's anti-cyclonic, it's the opposite direction. So it's taking things out from outside in the atmosphere and throwing them, sucking them into the column and slamming them against the ground. Okay, so our equatorial vortices are definitely anti-cyclonic. They're so if I've ever said that they were anything else, I was wrong. They're anti-cyclonic. Why? Because they're sucking things in from outside in toward the core of the planet. And I was thinking, well, if that's the case, then for the same reason that we have gamma ray bursts going out with both ends of the poles, then and that's emitting, then that must mean that the polar vortices are most definitely cyclonic. So they're sucking material out from the core of the Earth and spitting it out this way. Well, that could be possible. However, I'm going back on that theory. So due to centrifugal force and in addition to the coefficient of solar wind pressure drag, with a North Pole orientation like this, where you have your little red dot just slightly above the galactic plane, right? All of this material that's being slammed into at the front of the planet is being thrown back into that southward spiral, and so it might not have the chance to really develop a strong type of vortex that would be cyclonic. I'm not really sure I'm correct on that anymore, and here's the reason why. After looking at this particular vortex, it basically put me right down here onto this spiral density arm in in Antarctica. So what does that tell me, ladies and gentlemen? That's telling me that Antarctica did not have 4 spiral density arms at one time. That tells me that this spiral density arm right here is separate from this spiral density arm right here that cuts right through our current South Pole. So it's coming around here like this and actually goes up here and comes back around this way. So which one is more violent than the other one? Well, I'm going to throw this out there. I think that this one, with our current South Pole orientation, was by far more violent than this one. And the reason that is because this one seems to have very straight spiral density arms coming out of it. And the latter, on our current South Pole orientation. You can see it right there where it looks like all the snow comes and points right to the center. Those are a lot more like a rope wrapping around you. So that means that the continent, maybe not necessarily the planet, but the continent was rotating faster at the time the vortex was spinning free to spin. Okay, so there's two events here, and this one with the long, slower vertical rotation is related to this guy right here. And of course, you'll notice Antarctica is rotating in the same direction. That's how we know this particular vortex was closer to, undoubtedly closer to the North Pole than the South Pole. And for it to be closer to the North Pole than the South Pole, our polar location would probably be a little bit off from this vertical circle we have here, and more like right here. And then if that's the case, right here, right on top of that ridge, that would be just enough. Is that right? Or is that wrong? That's just enough to, no, that puts it into the South Pole. So in order for that vortex to have been above the equator, that means our South Pole orientation would have had to have been farther this way. And we kind of see how the South Pole as it sets right now is like, appears to be like right on top of these guys. Well, maybe not, because you're coming in through here and it sort of looks like it comes through here and back over here. So it's actually off from that center point that we have in the snow. That's only a Google feature. It's not really what the Earth looks like down there. All right, so for those of us who are not young enough to know that that's not natural. Well, anyway, so that would probably place our South Pole over here. Very complicated stuff. Anyway, it gives me the impression that these are two separate events, regardless. And if that's the case, now I'm going back to where I'm thinking about. I know I'm already dragging this out, right? Okay, so we have anti-cyclonic and cyclonic. Anti-cyclonic is pulling material in from outside toward the core of the Earth. Cyclonic is taking it from the core of the Earth and spitting it out. Well, I don't ever see any evidence on a North Pole orientation, on any one single North Pole orientation, not even the theoretical Caspian Sea North Pole orientation. This is, it's anticyclonic because it's a hole. It's not, it creates spiral density fractures. It's a hole. It's getting sucked in toward the center of the planet. The North Pole up here is definitely not giving you any kind of a mass that I can see at this point in time that is even closely relative to a spiral density arm. It's a hole. So that tells me that the Earth may only have one cyclonic vortex, and it just happens to be the South Pole. And all the other vortices are anticyclonic, sucking material in, primary vortices. Because now that we're thinking about that, if we come over here to Indonesia and whatnot, and down here by New Zealand, you see New Zealand then, if Antarctica is cyclonic, so is the New Zealand vortex. It's cyclonic. So is the Fiji vortex, the Fiji Island vortex. It's cyclonic. Why? Because it's pulling material out of the Earth. All right? And yeah, Papua New Guinea is more like just the top of some great big massive asthenospheric tsunami that came down, basically flowed down through here. It came all the way from the North Pole, did this little curlicue on the merry-go-round, and then came down here before it started to slow down into this region here. And it's that's, so you're looking at like a few right here, right? The South China Sea impactors Indonesian vortex right here is anti-cyclonic, because it's pulling material and it's sucking it into the earth like a drain. Put a hole there. Even if it is filling it back up after it put a hole in the earth. Put a hole, moved all that material out, made a nice big crater in the planet, like a nice big crater, like a planet-like sized crater. And then the earth wanted to fill that void back up, and in the process of doing so, became a vortex. All right, well, I wanted to cover those certain points, and I'm going to have to, before I go any further here, you see how my line just disappeared like that? I'm not convinced that's a Google Earth Pro issue. I'm more like leaning on, one, I probably have way too much stuff saved on my Google Pro. I mean, my computer's only big enough for so much stuff. And all this information I have over here in my places is very extensive. I have a whole bunch of drop-down lists. If I opened up every single one of these guys, boy, I tell you. Goose Lake, yeah, that's an impactor, but it's not the impactor I thought it was. That is not the impact. Yeah, well, that's a totally different story. Those are things that I'll look at later. I just haven't gotten around to it yet. Here's a whole bunch of stuff on Meteor Crater. But you can see how all that stuff piles up, and then you end up getting too much stuff, and your computer can't handle it. So, like, if I was to download this on my new computer, which is immediately to my left right here, and when I say this, I'm saying Google Earth Pro, it won't have anything. It'll be a clean slate. So it's all of this information is on the hard drive of my computer, as it would be with anyone's who has this program installed. So once you go to another computer, I haven't quite figured out how to transfer the information, but at this point I'm not really sure if I want to transfer that information, because if there's any kind of evidence for corruption, the last thing I want to do is transfer that corrupted bug right over to my brand new computer, right? So we won't do that, but we'll continue to use this one. I mean, it's good enough for me to figure out some stuff. Like, I'm supposed to have 2 red stripes going through here. You can't even see the southern red stripe. There it goes. Now my vortex down here, my vortex up here disappeared. I can't really do any kind of good evaluation or analysis when my lines keep disappearing. Not really. So now we have these lithostream scores coming right through here in the Indian Ocean. Very strong. Whether or not they're actually related to this guy here, I don't know. But when I scored them out, I counted the stripes, and and the number of stripes put this vortex in the stripe just underneath of the primary stripe at the equator, being it was up here. And so that to me was like, that's not possible. This vortex can't, it's not possible for this vortex to be related to those stripes unless my mapping of the stripes isn't necessarily accurate. I mean, there is room for error here, folks, but don't get me wrong. I'm onto something, and lithostreams do exist. I'm convinced of it. Otherwise, if they didn't exist, then why on earth, as they would like to say, right, do we have so many lithostream scores so strong up in here that actually maintain about the same interval, contour interval, as we like to call it in mapping, topography and stuff, all the way down here, you know. Like, no, that doesn't just happen, folks. Somebody didn't just come by with a seismometer and go, with a bunch of needles on their seismometer and go, okay, here I'm going to go around the planet, spin the planet. It didn't happen that way. All right. Anyhow, now, some of these lithostream scores that have been scored into the planet, some have been twisted, depending, maybe. I'm not going to say that they haven't, because like right here, it looks like they did. I mean, there's a lot of twisty things going on here. And then I just recently figured that this, that's where I started doing all this, was trying to figure out how I could map the mid-Atlantic ridge and look at it differently. Look at it as being the Earth's planetary suture, in which case that's very strong, because that goes in line with the Svalbard Islands having tropical plants. But how, to what extent, and when? And where was Antarctica at the time that this would have been the equator? Because it kind of would have cut right straight through the middle of Antarctica practically, right? Well, why not? Because it comes right up here, and bam, there's the North Pole, right? Right there, that little yellow dot. So it's like bam, right on the North Pole. So right there already we're looking at a axial tilt and polar migration that went at least 90 degrees from where it was when the planet finally solidified top and bottom and it's sealed together at the suture. We're looking at a very, very different Earth. And that would put, well, it doesn't exactly put this at the North Pole. Not at all. I'm pretty sure it didn't. Did it? Or did it? Could that have been the North Pole? Well, let's see. Okay, here's my theory, right? What if this was the North Pole? Well, okay, so the planet rotates in this direction. It's rotating, as we're looking at the planet on this view, if this was the North Pole, the planet would be rotating counterclockwise, and that means that this particular vortex would have been rotating clockwise. Is clockwise right? I don't think so. So if I'm standing right there on that yellow dot, and I'm spinning clockwise and I'm holding my rope is going to be more like Lake Victoria, because I'm spinning clockwise and my rope is going to be going around this way, dragging around my body. That's not the case here. This is the opposite direction. So no, this never could have been the North Pole. Yeah, I know. Are you thinking what I'm thinking? I'm thinking, oh shit. Does that mean it was the South Pole? That means that if that was the South Pole, and this was our planetary suture at the equator, this would have been slightly above the equator, because, if the South Pole is colder than the North Pole, then it would have solidified farther and faster, which would have put the suture above the equator. It would not have been an equal solidification process, right? And if that's the case, if that was the South Pole, that means the North Pole would have been up here somewhere. I don't have that one drawn in, so I'm like, well, that's a wild theory for you. So if that was the North, that would have made this the North Pole when the sutures came together. Then what on earth? How could the Pangaean North Pole, the whole idea of the Pangaea being at the North Pole, was based on the marshmallow theory. Huh. Things that make you go, huh? I gotta go, folks. All right. Well, good stuff. You know, I might not be the one to put the finger on it, but it's bound. And then that might, if that's the case, then that could possibly bring me back to maybe liking or at least reconsidering my view on plate tectonics. But at this point, my view on plate tectonics went out the window because you have the vortices. So it's got to be vortical tectonics. But how did the vortical tectonics make the continents migrate? There's your question. And the continents aren't necessarily plates then. They're just continents. They're like your kneecap floating over the top of your tube, your femur and your other fur. Or your femur and your other I forget what that one's called. And then it just goes in between and does this number, right? And then you have your synovial joint, or the synovial joints, your synovial membranes underneath of it. So, all right. Have fun, okay? Make sure you like this site and all you scientists out there, and subscribe. We get on this together, we might actually come up with some really interesting discoveries. All right, bye.